Hello everyone, and welcome to this new Copernicus Marine Service tutorial on marine data for sustainable oceans. My name is Alexandre Ombrun, I'm from Noveltis, and I will be your trainer for this Jupiter exercise. So today's topic is offshore wind potential in the European Northwest Shelf. So as you may know, in order to reduce carbon dioxide emissions, the world is slowly transitioning to renewable energy, and offshore wind power is one of the key players in the new sources of energy that are clean and don't emit any carbon dioxide. And so this offshore wind power has a great potential because winds are stronger over the sea than over the land, which is why it makes it promising sources of clean energy with high efficiency. But of course, when building a wind farm, there are several issues that must be analyzed before. First of all, of course, you need to build it in a location that has a high potential of energy production. So this is calculated based on the wind variability, of the dimensions and efficiency of the turbines that are used. You also need to conform to economic and technical constraints, installation cost, how to integrate the grid, how do you maintain such an infrastructure in a marine environment. And there are also environmental considerations. For instance, building a wind farm, of course, has an impact on the local ecosystems, but also on the human activities such as fishing or maritime traffic. And finally, some areas are subject to extreme weather risks, and those should be evaluated. And of course, if they exceed what a wind farm can withhold, of course, it can't be built in such an area. So today, in this notebook, we will try to use wind data and to model wind turbines in order to evaluate the potential for wind power production in several areas of the European Northwest Shelf. So we'll try to evaluate wind production and wind farm performance. So we will be working with Python. Here are a few libraries that are commonly used in such tutorials. We will use NumPy, which is the most common Python library to process data arrays. Pandas can also be used to process data tables or data frames. Xarray is the library that we use to open and manipulate scientific data in netcdf format, which is a standard used among the scientific community. SciPy is a Python library to compute statistics, regressions, process signals. Matplotlib and Cartopy are used to plot and draw the different maps and graphs in the notebook. And datetime is used to process time series, especially the datetime index of the series. So all those libraries should be pre-installed in your Jupyter kernel. So in my case, I'm on the Copernicus Marine Service Jupyter Hub using the version 4 of their kernel. And therefore, you execute in Excel, I can import all those libraries. Next, here's a brief overview of the product that we're going to use. So it's a combination of satellite observations and model outputs, which gives us this wind dataset. So it's a sea surface wind. So here you can visit the dedicated Copernicus Marine Service page and also consult the user manual or quality information document to know more about the product. But you can already see that it computes several observations from several satellite missions and uses also a model to correct some biases. And which leads us to this sea surface wind product that we are going to use. So in this overview, you can see the variables that we have retrieved from the product. So the two components, northward and eastward winds, and the air density that we are also going to quickly use. Here is the spatial resolution, so 0.125 degrees. And here is the temporal resolution, so we are using hourly data. And here the temporal coverage, but in our case we are only going to retrieve 1 year of data, because for instance we want to estimate the yearly production of wind power. So in the frame of this tutorial, 1 year of data will be enough for us. And with hourly data, if you download many years, you will have obviously 2 big files. So here's a brief section on how to access the data using the Copernicus toolbox. So in this paragraph, you will find some links to detailed articles on how to install the toolbox if you're not using the Jupyter, the Siemens Jupyter hub. In my case, I will just show you a quick method. So we will see that we will be using the subset function to retrieve data from this product. So if you're using the Siemens version 4 library, Jupyter kernel, you should be able to import the Copernicus Marine Toolbox, which in Python, in the Python API, comes under this name. So here I'm defining my area of interest, so defining a bounding box. So this, you will see, it encompasses the European Northwest Shelf. And this is a subset function, so it will, once you execute this, you see that here is the identifier of my dataset. If we go back to the dedicated page of the product and click on data access, you can see that this is the ID that we are going to use. Here are the variables that I've mentioned before, my bounding box that I've defined, and here the time range that I want to retrieve data from. So you can see here that we are retrieving all the data from the year 2023. And here is just the output directory, so it will be downloaded in data. I've already pre-downloaded the dataset, you can see it here. So we are already ready to go, but you can see that if you download the data yourself, it should go very quickly. So now the dataset is available. Let's open it and explore the file. So as you can see, it is a netcdf file. Hopla, it's quite long also. .nc. So what we want to do is to use xarray to open a dataset. So here is our dataset. You can see that we have our 3 variables here. It has 3 dimensions, so latitude and longitudes, and a time dimension. The coordinates are all listed here. And for each variable, you can, if you want, click on this icon here to find out more about the variable's metadata. There's the unit here, for example, a more detailed name or description of the variable, the minimum and maximum valid values, so this is quite handy. So first thing we do is a bit of pre-processing. So as you can see, our wind data is divided into 2 components. We want now to create a new variable which will compute the total wind speed. So basically, we are just applying this formula to our 2 components, just following the Pythagorean theorem. And this will yield the total wind speed over each coordinate. There is a lot of data to process, so this takes a few seconds. Okay, we are ready. And you can see that I have a new variable that is also dimensioned with latitude, longitude, and time. We don't have any metadata because we haven't defined any, but you can always add some when creating the variables. So let's now do some visualization and draw a wind field. So we have the total wind variable, so this will help us color the map. And using the two components, we will draw a wind field, so displaying arrows going in the direction of the wind. So to draw this map, we are going to combine two functions. So pcolor to color the map according to the wind speed, and quiver to draw the arrows, and their directions will be calculated using the eastward and northward component. So as you can see here, we're just choosing a random date to draw the plot. Here's the 25th of September 2023 at 9 p.m. Takes a few seconds to draw. One other thing we do here is that we coarsen the dataset, because we are going to draw an arrow over each pixel of the map, of the dataset. But if we do that, we won't be able to see anything because the pixels are very small. So coarsening the dataset allows us to interpolate the data and have pixels that are, in this case, 5 times larger than the original dataset. And you can see that this allows us to have fairly visible arrows. So here is a random date. You can see that the wind speed is quite higher here west of Ireland, and much lower here in the Bay of Biscay. So we have one field, but I want to show you now that you can also, with Python and Jupyter, perform animations of wind fields. So that's what I'll do in the next. Basically, I will redraw this map several times over consecutive time frames. So here we plot one map per hour over 2 entire days. So here my starting date is the 25th of September 2033 at midnight. And I will create a map for the next 48 hours. That makes 2 days. So you can see that I do exactly the same thing, the same map. I draw the coastlines. Here I do the color according to the wind speed. I set up the color bar. I make sure that for every map we have the same minimum and maximum values, because if you don't specify that, the minimum and maximum values of your color bar will be defined according to the maximum and minimum that are in the dataset. But for each map here, this might be different. So if you have a color scale here that changes at every hour, you won't be able to clearly analyze your results. Okay, it takes a few seconds because it generates 48 different maps. And here at the end, all those plots are saved in the out folder here. So I'm going to pause the recording and come back when all of this has finished. It has finished. You can see here that it's not a star now, it's the number of the cell executed. And now we are going to gather all the images that we have generated and merge them into a GIF image. And this yields this animation. And you can clearly see during the night following the 25th that we have a strong shift in the wind speed here in the direction of Ireland and the United Kingdom. And you can also see that this movement is quite consistent here with the direction of the arrows. So that's a nice map. Feel free to generate it over different dates, over longer periods of time. You have the method to do it now. Okay, so now we've explored the wind data. Now what we want to know is how much energy is this going to yield if we were able to install a wind farm in somewhere in this area. So in the next section, we're going to try to estimate the potential of exploitable power by the wind turbines. And the general formula to do such an estimation is the following one. So it is basically a function of the kinetic energy of the wind. So basically here the power is proportional to the air density, this is rho here. A is the surface area that is swept by the blades of the turbine. And here V is of course the wind speed that we have just computed here, that we just displayed here. And here this CP coefficient is a performance coefficient. So it accounts for the fact that the wind turbine doesn't convert all of the wind power into electricity. So it is generally between 0.4 and 0.5. So in this notebook, we'll define it as 0.45. So about the air density, we also have this variable in our dataset, so we will use it as such. And for the surface area, we need to take into account typical dimensions of a wind turbine. So you can do your own research, for example, visit a few pages. And so you can see here that, for instance, recent turbines have a diameter of approximately 150 meters. Future one should have 250 meters, so you can do research a little bit and do your own approximation. In my case here, I've chosen to have 100 meters long blades on my wind turbine, so as a radius, so it makes it 200 meters of diameter. This allows me to compute my surface area swept by the rotor. And so using this cell, we'll be able to compute the estimated converted power of a wind turbine over the whole dataset. Okay, so it has finished executing. I'm stopping here to make an important note. We here are doing quite a big approximation because our data here is sea surface wind. So it's wind data at 10-meter level above the sea level. But of course, a wind turbine sweeps the air at a much higher altitude, let's say roughly 100 meters. So of course, if we wanted to be clearly accurate, we should have used wind data at 100-meter level. However, the Copernicus Marine Service only provides sea surface winds, so we have to do with 10-meter levels. Okay, so now that we have computed this estimated converted power, let's try to find some potential efficient areas by computing the mean power over a year. So using the mean function of X-array over time, we can draw a map of the mean estimated power available in this area over a year. So we're drawing this map for that. So here is a power retrievable by one wind turbine in megawatts. And you can see that the further you are from the coast, the higher the power is, which is, well, kind of what we expected. You can also see that it's especially off the coast of Ireland that we have the most potential, also here in northern Scotland. And here in this screenshot of well, offshore wind farm projects, you can see that indeed over Ireland we have a lot of planned wind farm constructions, but also here near the coast of Scotland, which also has quite some potential here. So this is consistent with what we've just computed. So now I propose to you that in the next section we'll go a little bit further So in the next section, we'll take a closer look at how we can retrieve power from the wind. Because, as I've said before, we have hourly time series of winds. So we're going to use that to our advantage by trying to compute at every hour how much wind, how much power we can retrieve. So in order to do this, we are going to change a little bit the model with which we calculate the retrieved power. And in that regard, we will take into account the different operating phases of a wind turbine. So basically, this can be split into those four phases. So if the wind goes below 3 meters per second, it is too weak for the turbine to operate. So below 3 meters per second, a wind turbine doesn't generate any power. So then between 3 and 12 meters per second, the generated power is proportional to the cube of the wind speed. So here we are quite close to this formula that I've given to you just before. And between above 12 meters per second but below 25 meters per second, here is a nominal phase. Basically, the wind turbine generates its maximum theoretical power. It can go any higher than after 12 meters per second due to mechanical limitations. And above 25 meters per second, the turbine has to be stopped because the wind is too strong, and for safety reasons, the turbine must be stopped, and so it won't generate any power. So of course those thresholds are let's say usual or typical, but of course they change from one model of turbine to another, and they are usually given by the manufacturer of the wind turbine. So using all those thresholds and constants, we are defining this function power curve, which will return the power that is retrieved with regards to the wind speed and the different constants that we have defined. And finally, here I'm just defining a model for a wind farm. So maybe this is a little bit too early to show you this function, but it won't be difficult to understand. So basically, I just compute an area where I want to build my wind farm. Of course, I use the wind dataset as an input. I set up a model of the wind turbine that I'm going to use in this wind farm, and how many turbines I want to build in my farm. And I will explain to you afterwards what all those variables are for. So in the next cell, we are going to define an hypothetical model of a wind turbine. So we will use the wind threshold that we've mentioned above here, and we will choose a typical nominal power of 15 megawatts. So this value is usually, as I said, given by the manufacturer. And so, as I've explained to you, we are going to create a virtual wind farm on a designated location, so defined by the longitude and latitude, a chosen number of wind turbines, and well, the model that we have just defined. So it is defined here, you can see. Here we define our locations, and here we define the number of turbines in our farm. And it will use the power curve here in order to find the precise power output of our wind farm. So you can see that it uses the power curve function, okay, and in the end it is multiplied by the number of turbines that are in this wind farm. And here those are just flags that account for the operating regime the wind turbine is operating in. So whether it's at full speed, I mean at full power generation, so in this regime, or if it's on the partial load operating phase, or if it's in a zero power generation phase. So let's compute this to have the function active. Let's compute here our wind farm. So we've chosen a location, number of turbines, and our model. And now for the last figure, we are going to plot time series of the power output generation and compute for how long the wind farm has been operating at full power, and for how long it's been operating at zero power, and for how long it's been operating at partial power generation. And you can see it here. So basically here is the location of the wind farm that we have set up. Here is an overview of the operational phases. So partial operation means that the wind is between 3 and 12 meters per second. Nominal power is so the maximum power output generation. And here for 6% of the time almost, the turbines are not working due to either too weak wind or too strong wind. Here is a recap of the parameters. And finally, here is a computation of the amount of energy produced over a year. So this order of magnitude of approximately 1200 gigawatts per hour is actually enough to power a few hundred thousands households, so which is like a medium European city. And here in this time series you can see the power output of the wind turbine. So in dark blue this is full power, in light blue this is a partial load operation, and here in red the periods where the wind turbines don't generate any power are highlighted. And you can see here, for example, in 2023, that between, let's say, April and July, there is a clear here decrease in the wind intensity, and so decrease in the power generation. So if you do this at home, feel free to try to change the parameters here, change the location, change the number of turbines, for example, to generate this plot over another area. So the last thing we can do now is to compute the capacity factor of the wind farm. So as we said, it has generated approximately 1200 gigawatts per hour. And the capacity factor is the proportion of the energy generated with regards to the theoretical maximal production. So basically, if we had the nominal power production during the entire period. So what we have to do is to compute the theoretical maximum energy production. So we have so basically the number, the nominal power multiplied by the number of hours in a year, which is here 8,760. And if we do this, compute this cell, and you can see that we have a capacity factor of 0.46, which is in line with the usual capacity factors that we can see in real life. Yes, as I have precise here, typical capacity factors oscillate between 40% and 55%. So here we have 46%, so this is in the expected range. So we are reaching the end of this tutorial. You have a few exercises here if you want to dive deeper into this analysis. So I've mentioned some of them before. You can tweak the wind farm parameters in order to find out in other area how much power, how much energy you can produce, and in which regime the wind turbine would mostly work. Of course, you can download even more wind data to, let's say, analyze the production over other years or even several years. And we had the dataset here, sorry, was global, so you can always retrieve data with another bounding box to model wind farms in even outside of Western Europe. So feel free to do this. And this is the end of this tutorial. I hope that you have enjoyed it. Feel free to contact the the user support if you have any questions. And thank you very much for your attention. Goodbye.